So good morning and welcome to ESSERC 2025 Circuit Insights. I'd like to welcome all of you who are here today in Munich, and I would like to welcome all of you who are watching this recording later on YouTube channel, on SSCS YouTube channel. The title of my talk is Fundamentals of Circuit Design, but let me say up front that I'm not planning to give you all the fundamentals of circuit design in 1 hour talk. In fact, what we're going to do together with my colleagues is that we're going to kind of list all those fundamentals, but we're going to go and dive deep in several of those fundamentals. So hopefully you'll get something out of this at the end, but please do not expect one talk to cover all the fundamentals of circuit design. My name is Ali Sheikholeslami. I got my bachelor's in electronics from Shiraz University in Iran, and then I did my master's and PhD from University of Toronto in 1994 and 1999. And since then, I was a faculty member in the Department of Electrical and Computer Engineering at the University of Toronto. My area of expertise is in circuit design, analog and mixed signal. I worked in the memory area, memory design, that included SRAM, DRAM, FERAM, and MRAM at some point in my career. I also worked on high-speed signaling for chip-to-chip and backplane signaling. This is the area that is known as wireline area. And also, I worked on a stochastic search for global optimum recently. For fun, I organize this event, Circuit Insights, and also I write a magazine article called Circuit Intuitions, again in the Solid-State Circuit magazine. I also am the education chair for ISSCC. So why Circuit Insights? Well, the main purpose of having these Circuit Insights today and other Circuit Insights is to really share and spread the joy of circuit design among all the students and people in the field. The fact is that designing with these tiny devices called transistors can be really hard and daunting, because transistors are essentially elements that use electrons in order to control other electrons. This is what we are. We are in the area of controlling electrons. And as you know, although we have electrons all around, we can never touch and see any of them. So this is what I mean by this area being not as tangible. At the same time, the level of complexity has grown significantly over the last few decades. From the time when you were dealing with perhaps circuits that included just a few transistors to today when you can have billions of transistors on a single chip. The technology has advanced. Instead of having few micrometer of gate length, for example, now we're talking about 2 nanometer gate length. So we've gone down by a factor of 1,000. And remember, this is in one dimension. We've shrunk things by a factor of 1,000. If you think of the fact that this is two-dimensional, the shrink in terms of area is a factor of 1,000,000. So we've managed, in a matter of 50 years, to shrink things by a factor of 1,000,000. That's why you have, the cell phones in your pocket already has billions of transistors in it. So designing such circuits is very complex. Of course, if you want to resort to formulas, then they will be even more complex. And so the tendency may be that I just go to computer simulations. Or these days, the tendency is to go to ChatGPT and ask the questions and let them solve it for me. But that will take away the pleasure of understanding that we all want to enjoy. And so this is, although it is tempting to go to circuit simulation, really it is about you understanding and being able to do things relatively quickly and feel at home with the concept. So that is the purpose of Circuit Insights. And again, I must say that it's not just about pleasure. It's that if you want to go and innovate something, if you want to invent something, you cannot go to a new invention, new innovation, without having an intuition, an insight into that topic. So that is the purpose of what we do. So let me just spend a slide on circuit intuitions and circuit insights, and then we'll go into the actual talk. So circuit intuitions, as I mentioned, is the name of articles that I've been writing for the last 11 or so years. So I think we have at this point about 42 articles, and these are meant for undergraduate students and starting graduate students. So if you're interested in any of these topics, please take a look at this website, this link that I have at the bottom of this slide, and you can find all the 42 articles in there. So again, please take a look. Circuit Insights, we started about 3 years ago. I think it was ISSCC 2022. This was just around the pandemic, when we had the pandemic, and we decided to bring the students together. That first episode of Circuit Insights ran really well, and people asked us to continue. So then we took Circuit Insights to ESSERC. Later, we were asked to go to Asian Solid-State Circuits Conference. That's the sister conference in Asia. And also, we had CICC this year. So we have now been going through 4 conferences. These are 4 of the sponsored conferences by the Solid-State Circuits Society. And all the video recordings of those are available on SSCS YouTube channel. But for your convenience, I've also put them on the link that you see on screen. So that includes all the talks that we have had so far. So please take a look. Okay, so I said we're going to talk about fundamentals. Let me just categorize the fundamentals, at least from my perspective, into 3 categories. There are the basic theory that you need to understand. Those are fundamentals. We need to understand the basic theory. Then there is the concepts within circuit design. And if you go further, there are components, and these are building blocks that we deal with. So on the area of the theory, what I mean by that is, as you know, electrical engineering, or a particular circuit design, is really built upon a very strong background in physics. So we have a lot of theory that connects circuits, for example, to electromagnetics, or connects circuits to other concepts within physics, and that some of those will become circuit theory. For example, the basic concept of KVL and KCL, and then if you go further, you have Thevenin and Norton equivalent circuits. And then you go to transistor operations. There's a lot of physics behind those, but we try to make them a kind of an abstract understanding and make models for those transistors. This is part of the fundamentals that we have to understand. Then we go to concepts. You know, the general concepts will be power. We talk a lot about power. We talk about energy, talk about performance, we talk about area, yield, reliability, process variation, and power management. And the concepts in analog, we talk specifically about the concept of resistance. Most of you already know this. We have concept of transconductance, gain, bandwidth, feedback, all these concepts that form the fundamentals. And of course, when we go to digital circuits, delay become very important. Again, power, performance, area, yield, and reliability, which is common but maybe more pronounced in the area of digital circuit design. Now we go to major building blocks. So we're going to use the transistors to build amplifiers. And amplifiers is a major field. There are a lot of different types of amplifier you could design, and all of those will be within this category of building blocks. There's analog to digital converters. There's digital to analog converters. There's DSP, all the signal processing that you need to do. And also there's processors, accelerators these days. You may have heard a lot about AI accelerators. So these are all the building blocks that build on top of what we said. Then there's applications in wireline, in wireless, and also optical communication. There are many building blocks within these areas that form the fundamentals of circuit designs for us. And then we go to memory. And memory, of course, is volatile memories such as SRAM and DRAM. And then we have non-volatile memories such as flash memory. Now, among all these topics that I mentioned, there are some that are highlighted in yellow. Those are the topics that we're going to go today with the speakers that we have for it. So let me put it all together for the 5 talks that we have today. So circuit design sits at the center of this universe that I'm picturing here. And of course, circuit design is tightly coupled to electronic devices, to the technology that we're dealing with. So, you know, circuit design cannot be complete without the component that is sitting underneath. And that's what, if you remember, Christoph mentioned that ESSERC used to be ESSERC and ESSDERC. That was circuit and devices together in this conference. And it's because these two are tightly coupled. But with the circuit and underlying devices, we can enable many areas. So you can see circuit design could be related to memory design, for example. Memories are forming a major part of your cell phone today, your computers. Anything that deals with data and storage is about memory. So the good news is that we have dedicated 2 talks today. In fact, I will be talking about memory, but about volatile memory. And then Walter from Micron is going to talk about non-volatile memory, or flash memory in this case. Then we switch gear to analog circuit design, and this is Jens Anders, who is going to talk about feedback, one of the fundamental concepts in analog circuit design. And then we talked about power management on the previous slide, and the good news is that power management today will be covered by Bernard from University of Hanover and by Frank from Infineon. So we have all this expertise together today to cover essentially the right part of this, the right and top part of this diagram. But remember that the circuit design is much more than these. And again, I've listed those on the previous slide. You can use circuit design for the purpose of designing systems control, for the purpose of communication, whether that is wireline or wireless or optical, and machine learning, and of course, health. Some of those have been covered in the past, in the circuit insights in the past. So if you're interested in any of those areas, please go and look at the list of circuit insights talk and enjoy. Okay, so with that, let me start the outline of my talk specifically. I'm going to walk you through the very basics. So you don't really need to have too much background in this area. My assumption is that you're either third-year undergraduate students or above, and if you are in that level, you will understand everything that I say in my presentation. So please pay full attention. You will get everything that I say. Okay, so we start from basic planar transistors. I'll walk you through FinFET and gate-all-around transistors. And then I go to the very basic CMOS inverter and its voltage transfer characteristics. Then I will use CMOS inverter to build the SRAM storage cell. And then I will tell you how we can read or write into that SRAM cell. And I tell you the failure mechanisms that exist. And those are quite interesting. And how could circuit design that has all these failure modes could also be used to help avoid those failures. So that's the interesting part about this. So then I summarize, and I guess then we'll go to the next talk, which is about non-volatile memory circuit design. So these two talks are really nicely linked, hopefully, and you will enjoy them. So basic planar transistor is the one that is shown on the left. So I want to spend just a little bit of time walking you through this. So you can see at the bottom we have silicon substrates shown in gray area. And this part of this is source that you can see here. And there's this green gate that is on top. And behind that gate, there is drain area. So drain and source are essentially silicon area that are doped, for example, for NMOS with N+ region. And so the idea of a transistor is to use gate as a control gate or control mechanism for the connectivity between the source and drain. So the source and drain, if the gate, for example, is low for an NMOS transistor, the source and drain have no connection to each other. Essentially, this is an open circuit between them. But if you raise the voltage of the gate, you start to connecting source and drain. And that is the action of a transistor, in this case, acting almost like a switch. You have a controlling gate, and that controls the connectivity between source and drain. There are two parameters here that we often use. One is the W, which is the width of this transistor, and that's shown here. And then the other one is the length of the transistor. This is really the length of the channel, because underneath the gate, you will form a channel, and that channel has a width. Obviously, the larger width you have, the more charges could move, and therefore you can make a stronger transistor. But the other one is the length of the channel that electrons or holes needs to travel, and that is specified by L. This picture on the left shows what we call a planar transistor, because the transistor essentially, which is the source and drain, are sitting inside the substrate on a planar surface. And on top of that, you have a layer of gate, right? Now, what was the problem with this? By the way, we lived with this for over 50 years. So all the circuits that you've seen, and again today, many circuits are designed with planar transistors. But the issue is this, that the gate is really controlling the source or the channel that we have between source and drain just from the top, right? But there is no control from the side because the side is not accessible using planar technology. You have source and drain, and you have the gate on top. So the control is only exerted on the channel from one side, and that is not enough. We wanted more control. We wanted to be able to control the channel and have better transistors, if you wish. So this was the idea of moving from here to the right side, which is called FinFET. But before I go to FinFET, let me just spend a second on the actual symbol that we use for the transistor. This is a really nice symbol that, that kind of summarizes everything I said. You can see source on this end, it's shown in gray to match this, and you have drain on this other end, and you have this control gate that is coming at the top. And the job of the gate is to connect source and drain. But as shown here nicely, the gate is really controlling from one dimension, right? It's just trying to do it, the control from one dimension, which is from the top. If you go here to the right, which is FinFET, you notice the first major difference is that the silicon is now protrude out of the substrate. You call this a fin. So the fin is the silicon. The silicon here is coming out, and the gate goes around it. So on top, you have the gate. You can still control the top, but you also control this side and this side. The only side that you cannot control in this technology is the bottom part, right? So what have you done effectively is that, given the same footprint, which is the area, you have built kind of a high-rise. You have built the transistor vertical such that the gate could go on top and around this, and that effectively increases the W, the width of the transistor, because the channel is now controlled by the gate that goes around. So for the same planar area or projection in this dimension, you have increased the value of W. That means you've built a larger transistors using the same area. So this is the very basic of FinFET. I want to summarize. What we're saying is that you're using the same area of silicon, you have managed to build bigger transistors and have more control over the channel using the FinFET technology. So that's the basic of FinFET. Now, I have one slide to show you the cross-section. I want to make sure you all understand this because we're going to use this a bit later in this talk. And this is showing the cross-section of the same device here. With the blue here, blue essentially showing the channel that is formed under the gate inside the silicon, right? Inside the fin. The fin is this gray area, and the gate is here, and the yellow area is the silicon dioxide that's acting as a dielectric to separate the gate from the channel, and the channel in this case is formed is in blue, okay? So again, I want to emphasize 3 sides, larger W. Now, what happens when you want to build larger transistors? In the planar technology, you just increase W. The technology will tell you that the minimum W, for example, is 65 nanometer, okay, or 28 nanometer. Okay, that's the minimum width that you have to put in any transistor. But if you want to go from 28 to 30 to 35, 36, you could easily go. You don't have the granularity of going perhaps to 0.1 type of nano, but you have very good granularity. So from 28 to whatever you want to go, you can just increase the width. When we go to the FinFET, unfortunately, you don't have that choice anymore. In the FinFET, you can use 1 fin, 2 fins, 3 fins, or more. So all of a sudden, we have a major constraint in front of us. Now, obviously, there was something really good. We managed to build bigger transistors, but the granularity is now based on number of fins. So if you want to build a transistor with 1 fin, that is what you can see here, and the width of that, effectively, let's call that W. 1 fin gives you 1 W. If I want to go to 2 fins, I get 2 W. If I go to 3 fins, I get 3 W. So, but can I have 1.5 fin? Sorry, that's not an option. So you either have 1, 2, or 3. So this is what I mean by the transistor width that is now quantized in the FinFET era. To make the picture complete, let me just go back and show you what happens in the last, again, 50 years or so. So this is the planar technology. You can see the NMOS in here. We're showing the gate at color red and the gate for the PMOS color blue, just to distinguish the two, but in fact, the gate is the same gate. And it's a planar FET. It's been with us since 10 micrometer length of the transistor back in the maybe 70s to almost 28 nanometer. All of these were planar technologies. From 28 or 22 to 3 nanometer, we're using FinFET. And you can see the FinFET here. This is NMOS using 2 fins, PMOS using 2 fins. But for example, NMOS could have been using 3, PMOS could be using 2, whatever you like. But that's the structure. And that has brought us to 3 nanometer. And in fact, today, most of the designs that you're dealing with in advanced technology node, when people talk about advanced, they mean 3 nanometer, either TSMC or Samsung or Intel, companies that are providing FinFET. Now, this is not the state of the art. The state of the art, in fact, is the one on the right, this one, gate all around. So what is the gate all around? Remember, we said we have gate that are controlling the channel only from the top, that was planar. Then we brought it around and we said from left, top, and right. One more, we want it from the bottom too. And if you want it from the bottom, you have to turn the transistor, as you can see here, the silicon, here shown in green. This silicon, the gate goes all around. And this is called nanosheets sometimes. So you could put sheets of transistors on top of each other, 3 sheets, 3 layers, essentially 3 fins, but these are not fins anymore, these are gate all around. So this is 2 nanometer to 1 nanometer. We are, by the way, getting very close to the limits of this technology, because if you think about silicon, for example, the atomic distance between 2 silicon atoms is about 5 angstrom. And if you put 2 atoms or 3 atoms next to each other, you're dealing with 1 nanometer. So we're talking about controlling electrons within 2 or 3 atoms. So that's the state of the art of technology. In fact, today, most of the companies in the silicon or circuit design that are working on advanced technology node, they're using 2 nanometer, they're using gate all around or nanosheet or whatever you want to call them. Again, from companies like TSMC and Intel and alike. What is next? If we can build NMOS like many layers on top and PMOS like layers on top, why can't we make them on top of each other? This is going to be called complementary FET or CFET. And this is gate all around, but let's say NMOS sitting at the bottom and PMOS sitting on top. And that is going to give you, again, another advantage in terms of the area of the silicon that you use in order to build transistors. This technology is still in the research area, but I predict by the time that you graduate, you will have this accessible to you, right? So just on this point of the FinFET versus gate all around, not this just CFET. If I look at this, I want to just bring the point home that in fact, this was a paper that I'm citing here, number 5, that does a nice comparison between building a transistor using 3 fins. These are 3 fins in FinFET, and you can see that the footprint in terms of the distance is about 50 nanometer in this case. So this is FinFET. And then you say, let's just build the same, use the same 50 nanometer of distance and build nanosheets like this. So in other words, the idea of going from fins, which are vertical, to one that are horizontal on top of each other. What advantage do we get? And you can see, even though it's the same area or the same footprint, when you go to nanosheet, the effective width of this transistor is gone up by 30%. So use the same area, but you now have 30% more width of the transistor. So that is really the advantage that you will get. Now, I know that at this point you may think, wait a minute, I thought that electronics is complicated, but this seems to be even more complicated. Now I have to deal with fins, and I need to deal with gate all-arounds, and the concepts are going to be just building and become more complex as you go forward. But there's good news here. The good news is that because of the way things are organized, some of these are going to be relatively hidden from you as a circuit designer. When you go design, for example, a transistor or an amplifier, and you look at the layout is not specific to FinFET or to gate all around. From your perspective, you still see the effective width of the transistor that you want. How this is going to be implemented, of course, relies on the underlying technology that is going to be done by the foundry. So these are relatively hidden from circuit designers. Of course, you need to understand that there are fins, that the technology, you have all the PDKs available to you, but you really don't need to worry about it too much. The concepts, the fundamentals remain the same, and that is leading me to my next slide. So let's look at NMOS and PMOS transistors. Again, whether this transistor NMOS is done in FinFET or planar, it doesn't make a difference in the story that I want to tell you. And that is the very basic job of transistors, at least in the digital world and a mixed analog digital world. And that is that if I use an NMOS transistor here, You can see that this is a notation I'm using for VDD or power supply, and this is my input. And imagine that I'm trying to use this transistor to charge up this capacitor that is at the output. What I want to tell you is that NMOS is not a good pull-up. If you use an NMOS to pull this node from ground to VDD, you're not going to pull it up all the way to VDD. The voltage of the output is going to be stuck at somewhere which is a threshold below the gate. So if you have the gate connected to VDD and you wish to raise this node to VDD, by the time that this guy reaches to VDD minus the threshold, this transistor turns itself off. And so you cannot raise the output voltage. So that is what I mean by NMOS being a weak pull-up. You cannot pull up something. But on the other hand, it's actually a strong pull-down. So if you have the circuit and you want to pull down this node from VDD, and imagine initially this capacitor is charged to full VDD, and you would like to discharge it. If you apply VDD to the gate, you have VGS, which is 5 volts, always 5 volts, or sorry, 1 volt. You always have it at 1 volt. And what you do is you're going to create a current here, and this current is going to stay until you pull this down all the way to ground. So this is what we mean NMOS being a strong pull down. Similarly, you can look and find out that the PMOS, in fact, is a very weak pull down, but PMOS is a strong pull up. So if I connect this to 0 because this is PMOS, and I have 1 volt here, I always have the VGS or VSG control voltage that I need, and therefore I can pull this up all the way to VDD. What I like to do is to get the best of both circuits. So I'm going to use PMOS for pull up, and I'm going to use NMOS for pull down, and put them together to form the inverter that you have all been using, right? So I'm using a color code here to say this is the PMOS, a strong pull up, you have a strong pull down, and depending on the input voltage, either one of these is going to act as a pull up or pull down, and then you can therefore control the output voltage. And this is just shown symbolically as one of these symbols. Either this is an inverter symbol that you've all seen. The input and output are clear, but the VDD and ground are hidden from you, because if there are VDD and ground, you don't need to clutter your schematics, so you just don't need to show them. But sometimes you need to do some tricks to the VDD and ground. You want to switch the VDD and ground perhaps. So in those cases, you will just bring a line out from the top and bottom, and these two represents the connection to potentially VDD and the connection to potentially ground, and this is the output. If you look at the picture on the right, that shows you the voltage transfer characteristic. Now, depending on the input voltage, if you have input, for example, 0, then the pull-up is going to be active, and it's going to raise the output to VDD. At this time, by the way, the pull-down is off because the gate is 0. So this bottom transistor is doing nothing. Only the PMOS is going to pull it up. On the other side, when you increase the VN all the way to 1, then the pull-down will be active, pulling the output down to ground. And if you're somewhere in the middle, both of them are active, and essentially they're fighting with each other. One of them wants to pull it up, the other one wants to pull it down, and you may be somewhere in the middle. So really, I should be using a mixture of colors here in the middle because both transistors are active. Now, this basic transistor inverter is extremely useful in the circuit design. And in fact, just recently in the Solid-State Circuit magazine, and again, another advertising for that magazine, for you to please go and look at those. There are a series of 4 articles written by our colleague Behzad Rezavi that talks about 50 applications of inverter, just this 2 transistor circuit, and you can find their applications among many, many circuits in this area. So I encourage you to look at those if you're interested. Now, what I want to do is build with this. So I'm going to put 2 of these inverters back to back. Again, I'm now using a different color notation here. The top inverter I'm showing in red, the bottom inverter is in blue, and you can see there's a positive feedback going on here. So I've identified the left node as VL, the right node as VR, and then I would ask myself, so what is the transfer characteristic of the red inverter? And this red inverter is having VL as the input, which is here on this axis, and VR as the output, which is this axis. And again, this is the transfer characteristic that we saw in the previous slide. And what about the blue? Blue is actually opposite because the input is now VR, the output is VL, and to use the same graph, I just need to kind of tilt my head and say, well, this is the input and this is the output. Again, when the input, which is VR, is low, output is high, and output is here, so this is high. And when the input is high, the output is low, and again, this is low on this axis. So essentially, these are two symmetric inverter. Imagine they're identical, and they're done back to back, and we put them together. In steady state, or I should say at DC, if you have these two inverters back to back, there are you're trying to find a solution for VL and VR. These are the two node voltages that identify the states. And it happens that there are only three possible solutions because these two curves only cross each other at here, here in the middle, or at the bottom, right? So there are three solutions. Interestingly, two of these solutions, which this is 0, this is 1, or this is 1, this is 0, they kind of support each other, as you can see, and that corresponds to two stable states for this so-called latch. But there's another state in the middle, and that is when VL somehow comes to exactly half VDD. Again, I'm assuming that the two inverters are identical and symmetric. If you bring it to half, you can potentially have half VDD on the other side. So two half VDD can support each other, except that that is unstable. What do I mean by unstable? Well, you can potentially bring it to that point, but any amount of noise that will deviate one of the left voltage or the right voltage up or down a little bit, it will push it towards one of the other two stable states. And that is what I'm demonstrating here. If you look at the top picture on the left, so this is the original one, and imagine that I start at a state that's in the middle, but for some reason, the left voltage, I managed to add a bit of noise to it, a little bit to the right. What happens? Well, remember, the left voltage is the input to the red inverter. So this is the input now, and the output will become here. And this is now the input to the blue inverter. This is the input. This becomes the output. And this output becomes the input, and that will go here. So you can see this middle state, unstable state, sometimes people call this meta state, is going to immediately go to this state where the left is 1, the right is 0. What if I kind of deviate it or push it a little bit to the left, as you can see here? Then the same story happens, and you end up in the opposite state. So this is what I mean by the middle state being unstable. Now, what about these two stable states? Are they really stable? Again, for us to figure out if something is stable or not, first of all, you need to be able to be in that state, and then if you push it, it should come back to where it was, to where it was. And in fact, this is the case. Even if I push it so far as going from 1 volt on the left side to 0.6, well, 0.6 will be the input to the red inverter, and that will go here. This will become input to the other one and go here, and then you essentially go back to where you were. The same story happens here. If you push this voltage on the left all the way to 0.4, this still will go back to where you were, right? So this is what I mean by the stability of the latch. One question that comes to mind is that, okay, if I have this latch and I really want to destroy the data that is stored in it, can I do this? And the idea is that yes, in fact, you know, if I want to find out the limits, in other words, of how much noise can I add and yet maintain the data. And the idea is that if I add a bit of positive voltage here, let's say this is a static positive voltage. By the way, this we will find out later. This could come from, for example, process variation. The thresholds of these guys may change. And so you may actually have this static noise here. And to make the matter worse, I'm going to apply the same voltage but with negative polarity to the other side. So in other words, when you have the left voltage here, and the left voltage, let's say, is low, I'm going to add sufficient positive voltage in order to flip this inverter. And on the other hand, I also help by, of course, if I go high, this is going to go lower, but I'm going to make it lower even by adding another negative voltage. So I'm really helping to make this unstable and go backward. And the question is that, so what is that noise margin? How could you characterize it? And it turns out that this is related to the side of these largest rectangle, largest square that it can fit in this butterfly curve. And that is identified. So to explain this, let me just elaborate a bit more. So if I add a positive voltage to the input of this, from the perspective of VL to VR characteristic, you're really trying to get the input and pushing it higher. So the characteristic is going to go to the left. That is what I'm showing here. So if this is the original characteristic, by adding this n, depending on how much you add, you're going to shift this red curve to the left. And because the input to the blue inverter here is vertical axis here, if I add a negative voltage, this is going to be pushed to the up. So imagine that the red curve is going to go to the left because of noise, and at the same time, the blue curve is going to go up. At some point, when you increase these two will never cross each other anymore here. What happens here is that you lose one of the states. You just have one state. The only place that these two can potentially work is that the left side has to be 1. The left side will converge to 1, the right side will converge to 0, and that is where you stay, right? Because there's no other alternative. We just eliminated the other one. And you may think, well, this is a disaster if that actually happens. But I tell you, there's good news. We actually need this phenomena. Otherwise, we can't write into the cell. We need to read and write. And that is what brings me to the next topic, which is now we're going to use this latch to build an SRAM cell. We need to build a memory cell. And remember, for memory cell, something are essential. First of all, you need to be able to write into that cell, right? Write your data. And then once you write it, you need to be able to read from that cell reliably, okay? So that's what we're going to do, form a SRAM cell. And this is the basic of an SRAM cell. You can recognize now that what I've built so far is this latch in the middle, but I connected the 2 transistors on the side, and I connected to some lines that I explain what they are. So this latch in the middle, this is storing the data. Remember, one of the 2 stable states, 0 or 1. And then I have these 2, sometimes they call them pass gates, or call them access transistors, because they provide you access to the internal nodes of the cell that are storing the data. And I'm showing those in red. These 2 transistors are controlled by a line called word line. It's called word line because you just don't have only one cell, which is 1 bit. You're going to have many of these bits on the same row, and all of them are controlled by the same line. That's called a word line. Sometimes these word lines could be 1,024 bits. So when you actually access a cell, you're not accessing just 1 bit. You're accessing a page, which is typically 1,024 bits at the same time. But every individual cell that you're accessing, you need to look at individual cells, and those accesses are provided by bit line and bit line bar. So bit line, as the name suggests, is per bit. Every bit has its own line. But we use bit line and bit line bar. And let me just say up front that this is a misnomer. When you call it bit line and bit line bar, it doesn't mean that they are complementary. It's just 2 lines. They're called bit line and bit line bar. Sometimes they are complementary, but sometimes they're at the same voltage. So don't get confused on this. I was confused about this many years ago, why they're called bit line and bit line bar, but hopefully you don't have to go through this. So this is the same circuit. Now you understand bit line bar, concept of word line, and this is the full-blown transistor level picture that we have seen. So there should be no issues. I want to just add one more point, and that is this is known as 6 transistor SRAM cell for obvious reason, 60 SRAM cell. As I said, these cells are going to be put into arrays. So I just wanted you to have a mental image of that array before we move forward. So this is word line 0. This is word number 0 that has, let's say, 1,024 cells. This cell is symbolized here, and I put it inside the array. And I'm looking in particular on one of these columns. This is row 0, for example. This is row 1 and all the way to row number n. But then I'm showing you 1 bit of that. That's bit line 1 and bit line 1 bar. So I'm accessing, for example, word line 0. All these are being accessed. But then in particular, I'm going to focus on bit line 1 and bit line 1 bar. Okay? Okay, this is probably the most important slide. Of course, more important slides are going to follow, but this is the first very important that you need to follow, and I want to make sure that I spend time on this. And that is showing you the basic of read operation in SRAM cell. So how would I read? So when I say I want to read, that means I'm assuming something is written in it already. And for that, I'm assuming that this node, I'm calling it conveniently N0. It doesn't mean that this node has always have 0 in it, but for now, I'm assuming this node has 0 in it. This node has 1, right? 0 and VDD, okay? So that's the stored data. And I would like to access and I read it. I want to find out what is inside that cell. How would I do this? So the way to do this is by starting this circuit here that's shown as PC, that stands for pre-charge. What we need to do is, forget the bottom part of the circuit for now. What we're going to do is we're going to start with the pre-charge, and if I'm going to read this cell, I'm going to pre-charge both bit line and bit line bar to VDD. charge them both up. Remember, bit line and bit line bar are a misnomer. They can charge them both to the same value. They're both going to go to VDD. How do I do this? Look at these two transistors. This is the good pull-up. Remember, we had a PMOS, and you're going to make this PC go to ground. This is a pull-up. It's going to pull this node up. This is a pull-up. It's going to pull this node up to VDD. And then, in addition, we have this transistor here in the middle, which is equalizer. We want to make sure that not only do we pull both bit line and bit line bar to VDD, we want to make sure that the VDD is also equal. It's, you know, just extra caution to make sure they're exactly identical at the beginning. This is called pre-charge phase. So I pre-charge these, and this is even not shown on this figure. You can imagine it's just happening here before this time. And then what I'm going to do is I'm going to raise the word line. The word line is shown in blue here. The word line is going to go up, and that means these two transistors are going to turn on, connecting bit line to N0, connecting bit line bar to N1, and see what happens. Now, what do we expect to happen? What do we expect to happen? Let's start from the right side. The N1 is already at 1, VDD. Bit line bar is already pre-charged high at VDD. This is already high at VDD. The right transistor is doing nothing. It's just all is terminal voltage at VDD. The transistor essentially is off because you don't have a VGS. It doesn't do anything. So the one side is not doing anything. Doesn't do the read. The left side, the zero side, does the read. And you look at how it works is that this is now sitting at VDD, word line is sitting at VDD, bit line is VDD, but this N0 is grounded because of these pull-down transistor that we had here. So this is the data written to this is 0. Therefore, what happens to this transistor? Remember, we have the ground here, we have VDD here, and this is going to pull down the bit line. So the bit line is going to be pulled down on the right, and you can see it here, the bit line which is shown in green. Bit line bar doesn't change, but bit line is going to start to fall. And that falls because you have two transistors in series that are pulling the charge from bit line to ground. You just need to wait long enough for the bit line to fall below bit line bar, but by a good 50 millivolt, or let's say 100 millivolt. Once this is called the signal that is developed by 50 millivolt or larger, then you say, I now need to sense this. This is when you start this comparator at the bottom, or sense amp as we call it. You enable the sense amp, and this takes this as an amplifier, but a comparator essentially. Your amplifier is towards the VDD and ground. And then you get the data at the end, which is shown here on the right. Okay? So that's very straightforward. It seems we can easily read it, but I want to just tell you the pitfalls, and this is where the fun begins. So what could be the pitfall here? We assume that these two transistors are strong enough that when you do the work, this bit line is going to be pulled down by this guy because potentially we have a good transistor here, we have a good transistor here. But what happens if this transistor and this transistor become weaker? How could they become weaker? Well, when we build them, we intend them to be identical, but because of process variation, some transistors will have a slightly higher threshold voltage, some of them have a slightly larger threshold voltage or lower, and so some of them could be weaker with respect to the other one. There could be other effects that cause this, but let's just see what happens on that scenario. And to demonstrate that scenario, I've decided to put this gray area on top here. So this means that this transistor that is shown in gray, grayed out, is weaker. If these two transistors are weak, and the purpose, remember, was to get the bit line, which was charged to VDD, and discharge it to ground, it cannot discharge it as fast because the transistors are weaker. They are weak pull down, so they cannot discharge as fast. And so what happens is that if this was the original bit line going down fast, the weak bit line is not going to go as fast. And so by the time that you want to sense it, you do not develop enough 50 millivolt that you need for that sensing. And so what happens? You read the wrong value, potentially. Your comparator may not work, and then everything is going to fall apart. So this is the first read failure mechanism. But that's not the worst case. The worst case is when you try to read and you destroy the data. At least this guy didn't destroy the data. How could you possibly destroy the data? Well, imagine the case where you're going to connect these two nodes and you expect the N0 to pull down the bit line. But what if this is so strong, this transistor is so strong, and this transistor is weak, that instead of this guy pulling this guy down, this guy, which is bit line, pull this guy up? And when it pulls it up, it's going to switch. So you're going around the loop, and you're going to go to the other stable point. That is what I demonstrated here. So again, instead of just showing the weak transistors, imagine a scenario where these two transistors are weak, these two transistors are strong. And you may say, what is the possibility that that happens? It's actually quite possible. You have 6 transistors, and you can go through thousands of them. Some of them will have this scenario. And so what happens, and I strategically choose this combination for the reason that I explained. You see, when I try to, if when the N0 try to pull down bit line, right? Instead, bit line, this transistor is strong, this transistor is weak. It cannot protect N0. It let N0 go up. But as N0 goes up, this transistor is a strong pull down. It's going to help pull down this node, and that's going to be positive feedback, and it's going to destroy. And in fact, what happens is that if these are the internal nodes N1 and N0, during this read time, because this bit line is so strong, the two will flip, and this is called a stability failure in the read operation. Let me go to the write operation now. So write operation is a bit more straightforward, perhaps, because what you need to do is that you know that there's some data already inside. If the data that is already inside and this is what you're writing as well, that's not a big deal. But it's when you're trying to flip the cell. So imagine, again, I'm showing you symbolically that I have 0 stored here, 1 is stored here, and I would like to flip this cell. I want to write 1 to the left side, 0 to the right side. How would I do this? Well, it's easy. You need to raise the word line to 1, bit line bar to 0. So in other words, you want to write 1, you just do this. In this case, bit line and bit line bar are complementary. Or you want to do the opposite, you do this, right? That's the basic concept. Now let's see how that works. So again, if I have bit line going up, and that is bit line high, and then bit line bar going low, and then I will again raise the word line at this point. If I raise the word line, the bit line that is going down is going to pull the N0 down with it, right? Sorry, the bit line that is going up, in this case, bit line is up. Bit line is going to pull up the N0, and bit line bar is going to pull down N1. And if these transistors are sized nicely, and the strength is incorporated, so bit line will, in fact, manage to pull the N0 up to a level, and bit line bar manages to pull N1 lower, and they will bring them to that point where you cross over to the other side and you get the stable point. So that is the basic concept for the write operation. But similar to the read, there is a contention here, and that is when I try to pull down this bit line bar, in other words, the N0 down, this is the path. I'm trying to use this transistor to pull down the N1 to 0, but somebody's fighting me. And that is this PMOS transistor on the top. The PMOS transistor is trying to keep this N1 at high. That's why this is 1. This transistor is a strong pull-up, pulling it up. This one is trying to pull it down, and the fight between two becomes very important. So when I design this, I better design this NMOS transistor to be stronger than this PMOS transistor for the write to work. Otherwise, I can't write, because there will be a fight between those two transistors. But again, process variation could work against us. And this is a scenario where, in fact, if this transistor is weak, this is weak, and these two become strong again with some possibility, then let's see what happens. When I'm trying to pull this node down, this guy is so strong, it doesn't let me pull down the N1. And so when it doesn't let me, that's it. I will just go back to where it was. So you can see N1 is trying to go down, but it can't go down enough to switch with N0, so we'll go back to where it was. This is called a write failure. So under this scenario, you could have write failure, you could have read failure. And so what do we do in general? The general procedure is this. If you want to design an SRAM cell, this is something that has been known, by the way, for many years now, is that you design your pull-down transistor to be strongest among all the 3 transistors. By the way, this part is symmetric, it's the same one. So this is pull down, this is pass gate, and this is pull up. So we designed the pull down to be the strongest transistor, then it should be pass gate, and then it should be pull up. In other words, pull up is the weakest transistor, pass gate in the middle, and pull down is the strongest transistor. So this is the relationship. Pull down is weakest, pull up is strongest, and pass gate in the middle. If you follow this, generally speaking, You have the best of both worlds. You can do read and write. The only problem is we can't just make some guy a little bit stronger. It's a FinFET era. You either make it one fin, or you make it 2, or you make it 3. And so when I say this should be the strongest, well, probably it means you just use three fins. If this is middle, use 2. And if the other one is weaker, just use 1. So 1, 2, 3, right? And by the way, PMOS and NMOS have the same strength for the same fin in the newer technologies. So what happens? Let's just try 3 scenarios. And I want to vote afterwards in this class to see which one would you vote as a future engineer in this area. So first one is that this guy who is greedy, relatively, he says, I'm just going to use 1 fin for each. 1 fin, 1 fin, 1 fin. And this is also the same. This is actually known as 1, 1, 1. You just count 1 fin, 1 fin, 1 fin in this order. And then you go and characterize this cell, and you find out that actually this cell, this is how they characterize it. You just go in different dimensions. How does this perform in terms of density, in terms of read stability, read performance, write margin, leakage, and energy? And the greater that a polygon looks, the better is the cell, because everything becomes better as you go outward. So you can see density is the best, because could you go smaller than that? No, you just have 1 fin, 1 fin, 1 fin. Otherwise, you don't have a transistor. So this is the best density, right? But unfortunately, because this is not stronger than this guy, the read is going to suffer quite a bit, and read stability and read performance are going to be bad, both of them. The leakage is going to be good in this case because you've used minimum size transistors, but the write is also going to be bad. Why? Because this PMOS is going to be the same strength as this guy, and most of the time is going to win. And so you're not going to have a good read. So this is kind of, it seems out of the question, right? So let's go and do 1, 2, 2. Well, now I have made this one at least is stronger than this one, but these two are the same value. And if you look at this, immediately you see the density will get a hit. Why? Because you use 3 fins total here. I guess on the left side, 3 fin. This becomes 5. So you've increased it by 60%. You've added 60% more area, and now you get a SRAM cell that has a good, not as good density, but the read stability improved. Performance, write is really improved quite a bit, because now you're making this guy weaker than this guy. This is 1, this is 2 fin. Write is really good. Leakage and energy suffer a little bit, but overall you get much better shape than this. Now you say, okay, I still don't want this because I want to get better read stability. So you go to 1, 2, 3, as I mentioned, because that follows the original scheme. And if you go to 1, 2, 3, what you will get is this read stability goes back to where it was at the beginning. So, not back to where it's beginning, but the best you can get. Read performance, write margin, all of these good. Leakage, you suffer a little bit. Energy will be still good. And the density, though, goes down significantly. Why? Because instead of 3 fins, you have 1 plus 2 plus 3, 6. You've increased it by 100%. But you get very good response. So the question for you is that if you are the engineer, you're going to design this, which of these designs will you pick? 1 on the left, 2 in the middle, or 3 on the right? You use 1, 1, 1, 1, 2, 2, or 1, 2, 3. Remember, in one case, your read performance and read stability is really bad. Every time you read, you get an error, probably, or not every time, but a lot. This case, you need to pay for it a little bit, and in this case, you pay for it heavily, but you get really good results. So which one will you choose? How many of you will vote for number 1? 1, 1, 1. Can you just raise your hand? I see nobody. And for a good reason. Because say, what's the point of building something when it doesn't work? But guess what? This is the solution today. We are using 1, 1, 1. And I'm sure you're asking yourself, so how come? How could you ever make it work? Welcome to the world of circuit design. And I show you how it works. We go, and then we ask ourselves, wait a minute, I can make those transistors weaker or stronger, not by the fin size, but the voltage that I apply to them. I have word line here, I have bit line, and I have bit line bar, and I have VDD. Why don't I use those voltages to raise them or bring them lower and make the transistors that I want stronger? And by the way, when I know when I'm doing a read and when I'm doing a write, I go and target the right transistor, make it weaker. Right transistor, make it stronger, and I will always win. And that is the solution today, in fact. We go to 1, 1, 1, and we win. And so I want to show you some of these circuits. I know I have about 10, 11 minutes left. I'm going to use about 6 minutes of it to explain, but this is very easy. You will understand everything that I say. So let's go with the read assist circuit. I want to go with 111, and I want to make sure that this transistor, which was the NMOS transistor, remember, I need to make this guy weaker. Because if I make it stronger, I would destroy the read, right? I will write instead. That would read the stability. How do I make this weaker? Well, easy. Just make sure when you apply the word line to this line, you bring the word line a bit lower than what it was before. Just design a circuit. Instead of applying 1 volt VDD, apply 0.8 VDD to that point. That's it. This is the solution. And then you can see, if you don't do it, things are dangerous, and 0 could flip to N1, to 1. And then, but with this, you have very stable scenario. This is for write. How do I do for, that was for read. How do I do for write? The write assist says, oh, we can collapse the voltage of the VDD. This is an interesting concept. He says, remember what was fighting the write? This PMOS on the top. This PMOS wants to pull this up, and this NMOS wants to pull it down, and these two will fight. I don't want this guy to fight. What do? Cut off his VDD. Not completely, collapse it. Do this. Instead of applying a VDD which is going, you know, all the way, you bring it down. You make a notch in the VDD. Let PMOS die for a few, you know, hundreds picoseconds. And then you win. You write the right value, then you let him wake up. And that's it. You essentially slap him, you let him fall down, and then you make it work. There is a risk to all of this, by the way. For example, when I do a voltage collapse, this voltage, the VDD, happens to actually go vertically in the array. And if I take this VSCS, and then this is a collapse voltage, and I apply it to this column, this is the one that I'm targeting, which is good. I wanted to knock out the PMOS so that I can write into it. But what about these guys? Their VDD is going to get a dip. But not to worry, because there are all sorts of capacitances on those nodes. With a little bit of dip, the rest of them are going to be safe. No problem. But of course, we try it, and we'll see that there's no damage, and so we use it. I want to do one more on the negative bit line write assist. So to also make this transistor, the NMOS transistor, remember the NMOS transistor at the bottom of the cell has to be the strongest, right? If I want to make that strongest, one way to do this is to, when I apply the bit line voltage, I can bring down the voltage on the bit line to the negative voltage, not by much. So when I bring 1 to 0, I bring it to 0, but I go 100 millivolts below this. 100 millivolts is sufficient to make a particular transistor that I'm targeting to make that stronger. Now, unfortunately, I don't have enough time to go through the circuit, but the basic concept is that you're going to pull it down first to ground, and then through this capacitive coupling, you can couple some negative charge and bring it down to by about 100 millivolts, and that will target a particular transistor to be stronger again. Beyond all of this, we also have system level. So you have all of this circuit that you design, you do everything else that you do, but then some cells just fail so badly that cannot be helped. What do you do in that case? We're not going to throw away the entire memory that you've designed. What we need to do is to put spare columns and spare rows. So these are called redundancy. I know that many of you, when you buy a shirt these days, you see at the bottom there's 2 extra buttons. Those are redundancies. Just in case you lose a button, you go on a subway and you pushed and then you lose a button, you can just use one of those redundancies and replace it. So what we're going to do here is exactly that. So imagine that this column is bad. I want to replace this. So what I do, I make sure that I add another column. This is a spare column. And every time, when everything is okay, I just use all the green. But when something goes bad, I will use these muxes at the bottom, and I decide that I will choose the left column for all these muxes up to here. But from here, I use the right column. So that way, I eliminate this column completely, and I rely on these healthy ones, and I replace. This is just replacing one column. You usually have more than one redundancies for column. You have more redundancies for row, and that could help you with this. Finally, I thought I'd bring you one example of the latest SRAM that people have designed. I would have liked to bring that example from ESSERC from this year, but when I was preparing these slides, I didn't have that yet, so I just went to the latest one, which is ISSCC 2025. When I go to ISSCC 2026, I will use an example from ESSERC. So this is a paper done by our colleagues at Synopsys, I believe, Harold Pillow and John Barth and colleagues, and they made a 38 megabit per millimeter squared, 380 to 540 milliwatt dual rail SRAM in 3 nanometer FinFET technology. This is essentially a summary of the paper. This is the density that you could do today, and this is in the 3 nanometer FinFET that we discussed. And yes, they're using 111 architecture, and they're using dual rail. So they're using a power supply for VDD for digital and VDD for analog. And what they're showing in this graph, in fact, is that even if the VDD goes all the way to 0.4 volts and the VDDA goes all the way to 0.6 volts, the circuit is still functional. So you make it work under worst case scenario. And so that is this slide. With this, I would like to summarize this talk. We talked about the 6 transistor SRAM cell. We said that for good read and write, we need to have the pull-up being weaker than the passgate and then weaker than pull-down. We said, how do you avoid the read and write failure in the face of process variation, especially as you go to the FinFET? We said we can use circuits to circumvent technology shortcomings. That will be word line underdrive technique or VDD collapse that we talked about, and also negative bit line for the write. There's a lot more to be explored. In fact, every technique that I mentioned here has a circuit behind it, and this is the one that I would like you to explore on your own. These are the list of references that I've used, and these are the SSCS resources for you to explore on your own. The very first one is the Solid-State Circuit magazine. It's really a very good collection of articles that is written for this audience. So please look at Circuit Intuitions that I write, Circuit for All Seasons, or Analog Mind that is written by Behzad Rezavi, and the Shop Talk that is written by Chris Mangelsdorf. He was a former Circuit Inside speaker at this conference last year. There's a YouTube channel of Solid-State Circuits Society that includes everything that we talked about. There's a Circuit Intuitions in the magazine. If you want to find a quick link to those, you can just follow the links here. And of course, there's a resource center. There's many tutorials for the graduate students that you could go and enjoy. Finally, I'd like to acknowledge all my research group at the University of Toronto, the undergraduate students that I've had, the readers of Circuit Intuitions for giving me feedback, and the Solid-State Circuits Society for sponsoring this event and for many other educational activities. Thank you very much.